there is a volcano 87 kilometers from downtown Seattle as the most dangerous volcano in the United States. Not Yellowstone, not the volcanoes of Hawaii, not the recently erupting systems of Alaska, Mount Rainier, a 4392-meter ice-covered stratovolcano sitting directly above the most densely populated volcanic risk zone in North America, a region containing over 3 million people that serve the entire Pacific Northwest, critical military installations and infrastructure corridors. The reason Rainier holds that designation is not just the eruption risk, it is the lahars. Lahars are volcanic mudflows, walls of superheated water, ice melt, rock, and debris that travel at highway speeds down river valleys. With the consistency of wet concrete, Mount Rainier holds more glacial ice than any other mountain in the contiguous United States, roughly 35 cubic kilometers of ice and snow, sitting on an active volcanic system. When that ice meets volcanic heat, whether from a full eruption or simply from increased hydrothermal activity, it mobilizes instantly, catastrophically. The lahar valleys that drain from Rainier's flanks run directly through communities where people live, work, and send their children to school. Orting, Washington, a town of 7,000 people sitting in the Puyallup River Valley, of any populated place in America. And right now Mount Rainier is showing signs that it hasn't shown in decades. Most people think of Mount Rainier as a beautiful, snow-covered mountain, visible on clear days from Seattle and Tacoma. It is also dangerously incomplete. Mount Rainier is a stratovolcano, a composite volcano built up over hundreds of thousands of years, by alternating layers of lava flows, ash deposits, and volcanic debris. It began forming roughly 500,000 years ago and reached close to its current height within the last 100,000 years. Its most recent period of significant eruptive activity occurred between roughly 1,000 and 2,300 years ago, geologically recent, when it produced lava flows, ash falls, and the massive lahars that deposited sediment across the surrounding river valleys that communities now sit on. The last confirmed eruptive activity at Rainier occurred in the mid-19th century. Since then, the volcano has been in a period of surface quiet. But surface quiet on a stratovolcano does not mean the system is dormant. It means the volcanic activity is occurring below the surface, in the hydrothermal system and the magmatic plumbing that feeds it. Beneath Rainier's ice-covered summit, the hydrothermal system is one of the most extensive and aggressive of any volcano in the Cascades. Acidic, superheated hydrothermal fluids have been chemically altering the volcano's internal rock structure. The altered rock is weak, structurally compromised, and it sits at the core of a 4,300-meter mountain carrying 35 cubic kilometers of ice. It does not need to erupt catastrophically to generate a catastrophe. It just needs to collapse. Let me explain lahars in detail, because this is the mechanism that elevates Rainier above every other volcano in the contiguous United States. From a population risk standpoint, a lahar is not lava, it is not an ash cloud. It is a volcanic debris flow, a rapidly moving slurry of water, ice, rock fragments, and volcanic sediment. It fills valleys wall to wall, it buries everything in its path, and it can travel enormous distances from its origin point, far beyond the area where lava or pyroclastic flows would reach. The geological record around Rainier documents lahars that traveled all the way to Puget Sound, over 100 kilometers from the summit, deposited material across an area of roughly 550 square kilometers in the Puget lowland. It buried terrain that is now occupied by the cities of Auburn, Kent, and Enumclaw. The current ground surface that those communities sit on is the Osceola mudflow deposit. The people of the Puyallup River Valley are not living near a lahar hazard zone. They are living on top of the last one. More recently, approximately 500 years ago, a lahar called the Electron Mudflow traveled down the Puyallup River Valley and buried terrain that is now within the city limits of Orting. Orting sits in a valley so confined that there is essentially one road in and one road out. In a lahar event, the valley fills, the town floods with debris moving at highway speed, and the window between the lahar's departure from the volcano's flanks and its arrival at Orting is estimated at between 30 and 45 minutes. 30 to 45 minutes to evacuate an entire town of 7,000 people through a single road corridor. After whatever seismic shaking or explosive event initiated, the lahar has already damaged that infrastructure. USGS lahar inundation modeling shows that a major Rainier lahar event would affect not just Orting, but the entire lower Puyallup Valley. The communities of Sumner, Puyallup, Fife, and ultimately the port of Tacoma, one of the busiest ports on the west coast. It would sever Highway 167 and State Route 410, two of the primary highway corridors connecting the Seattle metropolitan area to its southern logistics infrastructure. The economic and humanitarian consequences extend far beyond the direct impact zone. For decades, Rainier's monitoring network has recorded a relatively stable background level of seismicity, hydrothermal activity, and ground deformation, active enough to confirm the volcano is alive, stable enough to maintain the lowest USGS alert level. The seismic network monitoring Rainier has recorded an uptick in earthquake frequency beneath the summit edifice in recent months. The events are small, magnitude 1 to 3 mostly, and individually unremarkable. But the rate increase, and critically the depth distribution of the new events, is what draws attention. A cluster of the new seismicity is occurring at depths consistent with the upper hydrothermal system, the zone where magmatic heat drives pressurized fluid movement through fractured rock. Hydrothermal seismicity of this type indicates fluid pressure changes in the system. Fluid pressure changes can precede both hydrothermal explosive events and, at higher intensity, the kind of phreatic eruption that volcanologists watch for as an early warning of deeper magmatic unrest. Gas monitoring at Rainier's summit crater and fumarole fields has recorded elevated sulfur dioxide output above the recent baseline. SO2 is a direct magmatic gas. It comes from dissolving magma, not from the hydrothermal system alone. Its presence in elevated quantities at the surface indicates that magmatic gases are successfully reaching the upper parts of the volcanic system. This is not unprecedented at Rainier. The volcano has always emitted volcanic gases. But the rate elevation above the established baseline is the signal that matters, not the absolute value. A system showing increasing SO2 output is a system where the gas flux from depth is increasing, and increasing gas flux means increasing pressure somewhere below. Aerial and satellite thermal imaging of Rainier's summit has identified localized areas of anomalous heat output at the surface, patches where the ice and snow are melting from below at rates inconsistent with surface weather conditions. These thermal anomalies are concentrated around the summit crater area and several fumarole fields on the upper flanks. Ice melt driven by increased hydrothermal heat output is significant for two reasons. First, it is a direct indicator of increased heat flux from the system below. Second, it directly contributes to the instability of the summit ice cap, the very ice mass whose rapid mobilization would generate the lahars that threaten communities downstream. A volcano simultaneously showing increased seismicity, elevated gas emissions, and anomalous ice melt is showing a coherent pattern of hydrothermal system pressurization. These are not independent, unrelated signals. They are three different instruments measuring the same underlying process. I want to go beyond the lahar scenario, which is already catastrophic, to address a risk that receives even less public attention. Mount Rainier's interior has been chemically altered by its hydrothermal system for thousands of years. The original strong volcanic rock of the edifice has in many areas been converted to weak clay minerals, principally smectite and kaolinite, that have a fraction of the mechanical strength of the original material. This process, called hydrothermal alteration, has effectively hollowed out sections of the mountain's interior from a structural standpoint. USGS researchers who have conducted detailed mapping of Rainier's altered zones have found that the weakened rock extends deep into the edifice, far deeper than surface observations would suggest. In some areas, the altered rock makes up a significant proportion of the material in the upper flanks of the volcano. A sector collapse, the sudden failure of a large section of the volcanic edifice, is a scenario that has occurred at stratovolcanoes worldwide. The 1980 eruption of Mount St. Helens was preceded by exactly this, a sector collapse that removed the entire north face of the mountain in seconds, exposing the pressurized magmatic system beneath and triggering the lateral blast that killed 57 people and flattened hundreds of square kilometers of forest. At Rainier, a sector collapse does not require a full magmatic eruption to initiate. A large earthquake, and the Cascade subduction zone sits directly beneath this region, could trigger collapse of a hydrothermally weakened flank. A significant increase in hydrothermal pressure could do the same. A collapse of this scale would instantly mobilize the ice cap above it, generating a lahar of a magnitude beyond what the current hazard planning is designed around. The current USGS lahar hazard maps for Rainier are based on modeled scenarios. A sector collapse scenario, a Rainier equivalent of St. Helens 1980, would generate flows that exceed those modeled boundaries. The people responsible for emergency planning in Pierce and King counties, the counties most directly in Rainier's lahar hazard zone, are not ignorant of this threat. They have been working on it for years, and their public communications, read carefully, are telling. Pierce County Emergency Management has formally identified lahar risk from Rainier as the primary natural hazard concern for the county, above earthquakes, above flooding, above any other geological threat. They have conducted lahar evacuation drills. They have installed a lahar detection system, a network of acoustic flow monitors and seismic sensors in the river valleys that would detect a lahar in progress and trigger automated warning sirens in downstream communities. The detection system is real and it is operational, but it has a fundamental limitation that emergency planners acknowledge directly. It detects a lahar after it has already left the volcano's flanks. The warning time it provides is the travel time between the detection point and the downstream community. For Orting, that warning window is estimated at 30 to 45 minutes under favorable conditions. Evacuation modeling for Orting has been conducted by researchers at the University of Washington. Their findings are sobering. Under realistic assumptions about traffic behavior, road capacity, and the condition of the road network following the seismic event that would likely precede or accompany a lahar, a significant proportion of Orting's population cannot be evacuated within the available window using current infrastructure. The solution is elevated structures built to withstand lahar inundation that residents unable to evacuate by vehicle could reach on foot. The vertical evacuation program exists. It is not complete, and the structures that have been built serve a fraction of the population that would need them in a worst-case scenario. The gap between the known risk and the completed preparation is not a gap that anyone in Pierce County Emergency Management is hiding. They will tell you about it directly if you ask. What they cannot tell you is when the gap will be closed, because closing it requires funding, political will, and public engagement. That has not materialized at the scale the risk demands. The USGS Cascades Volcano Observatory, the monitoring body responsible for Rainier, maintains the volcano at a normal green alert level. I am not challenging that designation. The current signals, while elevated above recent baseline, have not crossed the thresholds that the alert level system is calibrated to. But read the published research from the scientists who study Rainier most closely, the papers on hydrothermal alteration, on lahar hazard modeling, on edifice stability. And the language is consistent and direct. Rainier is not a question of if, it is a question of what kind of event and when. The scientific community distinguishes between eruption scenarios, hydrothermal explosion scenarios, and collapse scenarios. 3 separate pathways to catastrophe with different triggering mechanisms and different warning timescales. The eruption scenario has the most warning. The hydrothermal explosion scenario has less. The collapse scenario, triggered by earthquake, by internal pressure, or simply by the progressive failure of an already weakened structure, could have almost none. A volcano 87 kilometers from a major metropolitan area, with 3 distinct pathways to catastrophe, 2 of which provide minimal warning, sitting above communities with documented evacuation challenges. That is the situation the scientists are describing, and it is not getting the attention it warrants. Here is what I want you to take from this. Mount Rainier is not a distant, abstract geological threat. It is an active volcanic system showing current signals of hydrothermal pressurization, sitting above a lahar hazard zone that contains 3 million people, with evacuation infrastructure that emergency planners have formally assessed as insufficient for a worst-case scenario. The USGS alert level is green. I am not telling you to panic. I am telling you that if you live in the Puyallup River Valley, in Orting, in Sumner, in any community that sits in a lahar inundation zone, you should know your evacuation route. You should know where your vertical evacuation structure is. You should have a plan that does not depend on driving because the roads may not be functional when you need them. And if you live anywhere in the greater Seattle-Tacoma region, you should understand that the most dangerous volcano in America is not somewhere far away on a map. It is the mountain you can see from your window on a clear day. I'll keep tracking the seismic data, the gas emission readings, and the thermal anomaly measurements at Rainier as they develop. If the signals currently showing above baseline continue to escalate, you need to know about it before it becomes a headline. Subscribe and turn on notifications. Because with Rainier, the warning may not come with much time to spare.